This is Chapter 8 for Chemistry on Level. We are looking at covalent compounds, and for today what we're going to do is we're going to skip all the way to the back page. So we're going to look at the very last section of notes. So we're going to be right here. So if you skip all the way back to the very back of your notes and find the part that says Section 5, we're doing this. I'm skipping over Section 4 because this part, Section 5, is easier to do with me not there, and you can still get some of your notes taken care of. This one's a little easier to explain than Section 4. We will look at Section 4 when we get back from our break. So we're going to be looking at electronegativity and polarity. So that's what we want to consider, and so we're going to remember what electronegativity is. When we learned it originally, we learned it in our chapter on periodic trends. So electronegativity is the type of bond that's formed during a reaction, and it's all about the attraction. So if one atom is attracted to another atom's electrons, then it has a high electronegativity. So we talked about the trend. So when we originally looked at electronegativity, we looked at the trend. And so the trend for electronegativity is going to look like this. So the trend increases as you go up. It increases as you go to the right. But the noble gases are zero. The noble gases have an electronegativity of 0 because they do not want any other atom's electrons. They want to be by themselves. So what we're going to see for electronegativity is we're going to have a electronegativity chart called a Pauling scale. So this is the one that we're going to utilize. This is one that we're going to look at for our examples today. You have one similar to this in your homework. Homework number 4 has a scale similar to this. It's a little bit different, but it's the same idea. You've got the elements, you've got what their electronegativity is, and that way you can look at it and use it for what we're going to talk about. So this scale right here, you have a very similar one in your homework that looks like this. So it's a lot smaller because it only has certain elements, but it will help you for what you need it for. Also, this scale will be given to you on a test. So this, you don't have to memorize anything or anything like that. You just have to be able to use it. So basically what happens is we take and we look at the difference in electronegativity. And so if you think about math, difference means we're going to subtract. So we're going to subtract the electronegativity for the two elements in the bond, and we're going to see where it falls. So if the electronegativity difference is greater than 1.7, then the bond is ionic, or mostly ionic. If the difference is between 0.1 and 1.7, then is what we consider to be polar covalent. And then if it's 0, it's nonpolar covalent. So when we talk about the chemical bond and its bond character, we're going to determine that by the electronegativity difference. So like I said, we're going to subtract those two numbers and we're going to see where it falls. So before now, we always talked about that ionic meant that you had a metal and a nonmetal, and that covalent meant you had a nonmetal and nonmetal. And that's still true mostly. There are a few things out there that seem to be ionic, but because the metal is such a poor metal, that when you look at the bond character and you subtract, it's actually going to be polar covalent. So there are a few exceptions, but for the most part, we'll see that what we think about ionic and covalent stays true. So let's look at the difference between a polar covalent and a nonpolar covalent. So a polar covalent bond is where the electrons are shared unequally. So one atom is going to pull harder on the electrons than the other. one atom is going to pull the electrons closer to itself, and it's going to end up with a slightly negative charge. So, for example, if I put together, let's say that we had a bond between C and Cl. So we have one bond in between C and Cl. Now normally what we would see is that we are going to have two electrons in the center. Those two electrons are being shared. So I'm using the two electrons instead of the line, just because I want you to see that there are electrons there instead of having a bond. So, but what we see is if we look at the electronegativity, chlorine has a higher electronegativity, so the electrons are more attracted to the chlorine. So the electrons would be closer to the chlorine than they are to the carbon. So this means that there is an unequal sharing of electrons. They're not perfectly in the middle. And so this gives the chlorine a partial negative charge, and it gives the carbon a partial positive charge. This creates what's called a dipole moment. And so basically you get a partial positive and a partial negative charge. So they've got poles. So you have a negative side and then a positive side. So like poles on a magnet. We can also have something called a polar molecule. So a polar molecule is when you have things that are attached to the central atom that are different, or you have a lone pair. So we're going to look at the difference between a polar covalent bond and a polar covalent molecule. So here are two examples that we're going to look at. So we're going to look at HCl, and then we're going to look at H2O. So what I want you to notice is that this HCl is just one bond. We are just talking about one bond between the H and the Cl. And so we want to know if this is a polar covalent, a nonpolar covalent, or an ionic bond. So we're going to take and we are going to subtract the two electronegativities. So I'm going to go back to my electronegativity chart, and I'm going to find the electronegativity for hydrogen, which is over here. It's 2.2. And we're going to find chlorine, which is 3.16. So I'm going to take and subtract those. Now you never want a negative number, so you're always going to put the bigger number in first when you're subtracting, or you can think about taking the absolute value. I just like making sure I subtract the bigger number first. So we have 3.16 minus 2.2. And so we're going to subtract that right there. Sorry about that. My mouse got away from me. So when we do this, we're going to have 0.96 as our answer. And so 0.96 is going to fall in the category of polar covalent. So this is a polar covalent bond. Okay, then we're going to look at the same thing with our water. Now, with water, we have a bond that's happening between the H and the O. We have two of them. We don't care how many we have. We're just looking at the bond between those two. So we want to look at the numbers. So we're going to look at H, which we know that H is 2.20. So now I want to find what O is. So I'm going to go back up. I'm going to look at O, and it's 3.44. So we're going to subtract those two numbers. So we're going to do 3.44 minus 2.20. And we're going to get 1.24. So this is, 1.24. This is still in the range of polar covalent. So this is polar covalent. We also can evaluate the whole molecule. So this one over here was just one bond, so we don't have to do that for this one. But for this one, we can look at the whole molecule. So let's draw H2O, and let's look and see what it looks like. So remember, we're going to do our numbers. So 2 times 1 plus 6, that gets me 8. So we're going to put oxygen in the middle, hydrogen on either side. So we used up 4 electrons in our bonds. That leaves me with 4 left over. Hydrogen doesn't need any more, And so we're going to put our leftovers on the oxygen. So oxygen has 2 lone pairs, okay? So the way we look at a polar molecule is we look around the central atom. So when I look around the central atom, I see a bond, a lone pair, a bond, a lone pair. And so what I'm looking for is to see if everything is exactly the same around that central atom. So if, for example, we had oxygen with 4 bonds around it, and everything was bonded to the same thing. So let's say we had oxygen bonded 4 times to hydrogen, which this never happens, but let's pretend for a second. See how everything around this is exactly the same? It's identical all the way around. That would be nonpolar because everything is equal going around it. Nonpolar means there are no poles. Nothing is being pulled stronger. Everything is equal. We don't have that though. What we have is we have a situation where we have oxygen, we have 2 hydrogens, but then we have 2 lone pairs. So those lone pairs are going to pull differently, and so you're going to end up getting poles or areas. Some areas are a little more positive, some areas are a little more negative. So this is called a polar molecule. So sometimes you're asked to look at the bond, which is here. Sometimes you're asked to look at the molecule, which is here, okay? Let's compare that to a nonpolar covalent bond. So a nonpolar covalent bond is where the electrons are shared very equally. So for example, if we had chlorine bonded to chlorine, and remember I'm using the electrons here instead of using the line so you can see the electrons. In this case, we have identical atoms, and so the pull or the electronegativity is going to be the same. So the electronegativity difference is 0, which means that the electrons are being shared perfectly equally in the middle. And so that means it is a nonpolar bond. For a nonpolar molecule, you would want to have an atom, and then everything attached to the atom is exactly the same. So everything around the central atom is exactly the same. Okay, so let's look at some examples here. So for our examples, we have H2. So this means we have an H bonded to an H. And so if I do the electronegativity difference, 2.20 minus 2.20, and so I get 0 on that. So that is not going to have a difference of electronegativity. So the electronegativity difference is 0. So this is a non-polar covalent bond. Okay, for the CH4, we're going to look at one bond. So we're going to look at one of these and look at just one of the bonds, and then we're going to look at the molecule as a whole. So for carbon, let's see what carbon is. Carbon is 2.55. So we're going to do 2.55 minus 2.20. And so if we subtract this, we're going to get 0.35. And so this is a polar covalent bond. But now we want to look at the molecule as a whole. So we're going to take this and we're going to draw it. So C is 4 plus 4 hydrogen, and we know that hydrogen is 1. So that's 8 total bonds. We're going to put a carbon in the middle and then 4 bonds to hydrogen. So hydrogen, 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 hydrogen. When we look at this and say how many electrons did we use in bonds? 2, 4, 6, 8. So we have 8 electrons in bonds, and so we used up all of our electrons. The carbon has 8 electrons around it. The hydrogen has what it wants, and so this molecule is drawn. Okay, this is how the molecule should look. So if you look around this, all of the things around the central atom are exactly the same. So everything around the central atom is the same. So this is a non-polar molecule. So you can have a polar covalent bond in a non-polar molecule. Now, you don't have to write this, but let me show you something here. So if I would have taken, and for example, if we would have had a different molecule, and instead of an H right there, we had a Cl. This would be a polar molecule because you see how everything is not identical around it. Okay? Likewise, if we had had, let's put our H back there, if we had had, instead of an H right there, if there had been a lone pair right there, then again, this would be a polar molecule because there's not everything around it is the same. So it is nonpolar because everything around it is the same. Okay, the last thing here, this is just the last little thing in our notes. It talks about ionic bonds. Remember, we've talked about the ionic bonds transfer electrons. An example of an ionic bond would be NaCl. If you take and you subtract, so if we do Na and Cl, just to double check this, see if it works. So if I go all the way back up to my electronegativity chart, we're going to see Na is 0.93 and Cl is 3.16. So if we put that, 3.16 minus 0.93, and so if we do this, we are going to get 2.23. So you can see that this is greater than 1.7, so this is definitely an ionic bond. And it should be, because if you think about it, this is a metal, this is a non-metal, so this definitely should be an ionic bond. Okay? Okay, so here's what you're going to do. There is a bonding practice worksheet that you are going to complete and turn in today. And then when you are done with that, then you are going to work on your homework packet. Specifically, you can go now to homework number 4. And this is a really easy thing to do. It's a really easy assignment to do. You have your electronegativity chart here. And so we're going to take this and we are just going to write down the electronegativity of one element and then the other, and then subtract and find the difference. So for example, if I'm going to take and do this right here, which is H2O, now the 2 does not matter because I'm just looking at one of the bonds between the H and the O. And then I would go up here and I would look for H, and I would see that H is 2.1. So that's my first element is 2.1. The second element, O, is 3.5. And so I'm going to subtract these two. Now remember, I never want a negative number over here for my difference. So you've got to think, okay, I'm going to put the bigger number in first when I subtract. Or you can think, okay, I'm going to take the absolute value. So no negatives. So the difference is 1.4. And so the bond type is polar covalent. So because it's 1.4, it falls between 0.1 and 1.7. So it is polar covalent. Okay. So you can work on this. Now remember that you should have all of homework number 2 done, and you should have the first column of homework number 3 done from this week, from us working on Wednesday and Thursday. And so now you can work on homework number 4. This should not take you long at all. Okay, have a good day.